some questions I've been asked about Lecture 1. And so let me just make some general comments. One question I've been asked a couple times is I mentioned sort of tube formulas and kinematic formulas for PL manifolds, and those are manifolds without boundary. What happens if the manifold has boundary? And that's also part of the classical story, which I just didn't mention last time. But in the classical story, in the story we told, we got the Lipschitz killing curvatures for the manifold. And if the manifold has boundary, you end up with extrinsic measures of the curvature of the boundary sitting inside the space. And the first one was due to Steiner. It was a combinatorial formula for mean curvature of one PL manifold sitting inside another. And then there are higher order extrinsic Lipschitz killing curvatures, which are all dealt with by Cheeger, Mueller, and Schrader in their really beautiful paper on the subject. So I recommend you look at that if you're interested. The second question I've been asked a couple times is I presented at the end of the lecture a notion of combinatorial Ricci curvature that had somewhere in there a combinatorial Bachner-Laplacian, which is very closely related to the Levi-Civita connection. And once you get that, you have all of Riemannian geometry. So why did I stop with Ricci curvature? Why didn't I just present combinatorial Riemannian, a complete theory of combinatorial Riemannian geometry? And the reason is it's true that if you believe it, that there's, we have a notion of combinatorial Bachner-Laplacian, and the Levi-Civita connection is some sort of square root of that. The problem is you can try to go further, and Karsten Lange, who I mentioned last time, has thought about this, and you can talk to him about his work. The problem, as I see it, is there are too many square roots of the Bachner-Laplacian. I mean, you can define all sorts of things. And there's a lack of guidelines. Like we use the Bachner-Weizenbach formula or an Gauss-Bonnet theorem or something like that. To my mind, there aren't any clear roadmaps on which definition is the right one to follow. It's not clear what facts from Riemannian geometry we should be trying to duplicate in the combinatorial setting to get a more complete theory. And the last thing I want to mention, I mentioned in the answer to the question, but I want to emphasize that there's a paper called on combinatorial Ricci flow on surfaces, or something like that, by Ben Chao and Feng Luo. And it's a very different sort of Ricci flow I've been talking about, but it's closely related to, in fact, it's intimately related to sphere packings, circle packings on surfaces. And it's kind of a combinatorial differential geometry approach to circle packings. So it really fits in well with the sort of the theme of this workshop, and I recommend you look at that if you're interested. Okay. I want to start by saying something about Garland's approach, which I promised you last time. But I have to take a step back and remind you that at some point in the middle of this whole procedure of going from, say, the cochain complex to a combinatorial Laplace operator, we had to choose inner products. So let's just say a word about inner products. We're trying to choose an inner product on the cochain space. And it's quite natural when you're defining an inner product in cochain space to declare the cells to be orthogonal. But that still leaves you a little leeway. You get to choose a size for each cell. So in natural class of inner products, you get a natural inner product if you give a positive weight, W of alpha for each, I say simplex, but in general, for each simplex alpha. And then if you have two cochains, you can define the inner product of the cochains by doing the natural inner product weighted by the weight alpha. Okay. It says now we present two different combinatorial analogs of Bachner-Weizenbach. One of them I did last time. You're seeing the slides slightly out of order. Okay. And what I want to show you now is just a tiny view of Garland's approach. To do it justice would take an entire lecture by itself, and I really struggled a bit to see how we could see something about this method without going too far off track. So what I want to tell you now is a very special case of Garland's approach. And in fact, what we're going to do is sort of a facet of Garland's approach that was presented by Borel. And the precise theorem we're going to present is due to Wang. And there's been a lot of work on this method in the last 10 years, from Zhuk, Ponsu, and the others, are all in the last 10 years. So there's been a real kind of resurgence in interest in this method. And I'll say something about what they did at the end. So let's start with M as a connected, finite, m-dimensional simplicial complex. And the link of every vertex is connected. Now, to do this on a general simplicial complex, you have to choose a very special set of weights. It doesn't have to be precisely this weight, but something like it. So this is a very strange weight. Attached to the weight of a p-simplex is some constant times the number of maximal dimensional simplices which contain that simplex as a face. Okay. It's a kind of a strange formula, but the point is this relationship, that the weight of a simplex is the sum of all the simplices in one dimension higher that contain it of the weight there. And you'll see where this kind of relationship sort of plays a role. And then, given any vertex, we can assign weights on simplices in the link by, if you want to, if a beta is in the link of a vertex v, thought of as an element of the link of v, you assign a weight where you just join it with v. You get a simplex to dimension 1 higher in the star of v and take the weight of that thing. Okay. So now here's a theorem due to Wang, that a very recent theorem, in fact, we can just state without doing much more work. So for any vertex v, let kappa of v denote the smallest positive eigenvalue on Laplacian 0. So that's the Laplacian on 0 cochains. We declared the link to be connected, so there's only one 0 eigenvalue of the Laplacian. The number of 0 eigenvalues of the Laplacian is the number of connected components. And then the next eigenvalue is positive. So kappa is a positive number. Kappa of v is a positive number. And let kappa just be the infimum of those over all the vertices. And now let lambda 1 denote the smallest positive eigenvalue of the Laplacian on the whole complex, acting on 0 cochains. Okay. Then the theorem is that this lambda 1 is bounded below by 2 minus 1 over kappa. Okay. So this is the flavor of the sort of result that comes out of Garland's approach. That we have a notion of local curvature, which in general will be an operator like this. It will be a Laplace operator acting on the link of a vertex. So the curvature operator at a vertex is a Laplacian acting on its link. This is a commonality running through these approaches that are based on Garland's approach. And if you want to bound the curvature of the link below, you can see the larger the curvature is of each of these vertices, the better the bound is you get on the eigenvalue. So this particular statement is not a cohomological statement, because it's about Laplacian on 0 chains. But it's got the flavor of the results that Garland proved.
Why do you refer to eigenvalue as curvature?
By analogy with Bachner's method. So in Garland's approach, he wasn't studying the eigenvalues of Laplacian on 0 chains. He was studying the eigenvalues. He wanted to study the kernel of the Laplacian on p cochains, and you just want to know the smallest eigenvalue is positive. You get a bound something like this, so that if you have a good enough lower bound on the curvature at each vertex, you can conclude that the smallest eigenvalue is positive, and therefore there's no cohomology. So that's the outline of the approach. Garland, in his original work, studied spaces with lots of symmetry, namely Tits buildings for various groups. And in that case, we didn't need these special weights. The cancellations all occurred naturally. And it was Borel who observed that the method worked for general simplicial complexes if you chose these special weights. And he, like I said, he studied Laplacian acting on p cochains for all p. And by estimating the curvature, he was able to show in a lot of cases some really amazing vanishing theorems for cohomology of p-adic Lie groups. And the other work that I mentioned extends this to show property T for various groups and rigidity of group actions and all sorts of other things. So it's been, in terms of applications to, in some sense, the rest of mathematics, it's really, I think, one of the most striking applications of sort of combinatorial differential geometry. Okay. And now I just want to show you one formula. From the last lecture, we talked about, this p curvature on simplices, which is the number of things it was the face of, plus the number of faces, minus the number of parallel neighbors. There's a corresponding formula for curvature for general weights, and I just want to show you the formula. So if you choose general weights for the simplices, here's the p curvature of a p-simplex, where before we just counted the number of betas that contain alpha. Here we count them with some weights, right? And the same for the guys which are contained in alpha, and here's the rest of it. Anyway, I just want to show you what the formula looks like. That you can write down an explicit formula for general weights, and it's not too complicated. Okay. And again, this just comes from writing down the combinatorial Laplace operator in kind of local coordinates. I mean, just writing it down in terms of simplices, and then just counting up the diagonal terms minus the absolute value of everything else on the row. Okay, so that's kind of finishing up topics from the first lecture. And are there any questions, comments about that? Okay, so the last topic that I want to talk about is in terms of connections between, where we might look to find combinatorial versions of curvature or functions of curvature which integrate to give topological invariance. So here's a question we can think about that's closely related to a question that was asked last time. Suppose I give you, for each vertex, I give you the star of the vertex, separate. I don't show you the original complex. I just show you the star of each vertex as an unordered set, no labeling. Okay, I just give you a collection of stars. And then the general question is, what can you tell about the manifold from just that, collection of stars? In terms of the functions of curvature which integrate to give topological invariance, here's a more precise question. Suppose you have a function on the space of stars. And what you're allowed to do is evaluate that function on each of these stars and then add them up. Okay? What kind of topological invariance can you construct that way? Okay. So what functions on the space of stars, if you go through this procedure, always result in a topological invariant? Okay. So one we're already familiar with, and that's the Euler characteristic, can be expressed in this way. So let's just go through this. We did it in the case of surfaces to begin the first lecture. Now let's do it in the case of higher dimensional manifolds. So we know if M is a compact triangulated n-manifold more generally, but this is the kind of thing we're interested in. Then we have a formula for the Euler characteristic in terms of the alternating sum of the number of I-dimensional simplices. In the Riemannian category, there's a formula for the Euler characteristic in terms of the Pfaffian of the curvature matrix. So let's just go through this quickly because there's one ingredient in this proof that I want to emphasize. So what do I mean by the Pfaffian of the curvature? As we mentioned last time, I just review it here. In this world, you should think of the curvature as a skew-symmetric matrix of two forms. Okay? And if you're an M manifold, it's an M by M matrix. Okay? What can you integrate over an M-dimensional manifold? You can integrate M forms over an M-dimensional manifold. So from this matrix, which is M by M, matrix of two forms, we want a polynomial that's homogeneous. We want a polynomial that's homogeneous of degree M divided by 2 in the entries. So that when we evaluate that on the entries of the matrix, all of which are two forms, we'll get an M form, and we can integrate it. So what's a good polynomial of the elements of a skew-symmetric matrix that's homogeneous of degree M over 2? Well, one is the Pfaffian. So what is the Pfaffian? If you look at the determinant of a general skew-symmetric matrix, and I'll just put in variables on the off-diagonal entries, and you look at that determinant as a polynomial in the entries, you'll see that it's the square of a polynomial of degree half the dimension. And a Pfaffian is a choice of a square root. Okay. But now we just made a choice, and that's a little troubling, right? Because the square roots are plus or minus. Okay. Well, a choice of an orientation on M gives you a choice of one of these square roots. Before we can integrate an M form over an N manifold, we have to choose an orientation for the manifold. And choosing an orientation changes the answer by plus or minus 1 also. Okay? And in this case, those two choices cancel out. So that's a crucial point. That when we choose an orientation, it makes a choice of a Pfaffian, and it also makes a choice of sort of a rule for how to integrate. And those two choices cancel out. So what we end up with is independent of the orientation on the manifold. In fact, you can do all this locally, so the manifold doesn't even have to be orientable. But you can just see from this argument that this is actually kind of a subtle thing, and somehow orientations will play a role. So later, when we introduce them in a more direct way, you'll see that they actually were kind of here, but hidden. Okay. And now let's make this formula look a little more like this. And what I mean by that is what we talked about at the beginning of yesterday. Let's change this into something that looks like the sum over vertices of something local. Okay. So we know how to do that, actually. Here's actually a picture describing some words that I've already used. Given a vertex V, a star of V is the smallest neighborhood of V that is a subcomplex of your space. And the link of V is the boundary of the star of V. It's the set of things in the star which don't actually contain V. Okay. And I claim that this formula is the same as the formula I wrote before. Right? And why is that? Well, we want to count, for example, an I simplex in the complex with a minus 1 to the I. Right? Well, an I simplex in the complex, if we take an I simplex here, it shows up as an I minus 1 simplex in the link. Okay? So when we sum over simplices in the link, we have the exponent of the minus 1 is off by 1. I should have said, because an I plus 1 simplex over here shows up as an I simplex in the link. Moreover, we're counting things too many times, because an I plus 1 simplex here shows up in the link of I plus 2 vertices. Right? So we have to divide by I plus 2. Okay. So this is the formula. So we can sum over all vertices this function on its link. So now, just to make it look sort of consistent with what we'll do later, define this function on simplicial complexes or on links or whatever. Define this function on simplicial complexes, which is exactly what I had up here. And now we have this fact that now the Euler characteristic is equal to the sum over vertices, this function that just depends on its link. Okay? So this is now an integral over the manifold, if you like, of some local function. So this is the combinatorial Pfaffian. Is there?
Yeah, is it local with respect to vertices?
By local, what I mean is it just depends on the star or the link either. Yeah, that's.
Star over vertex, right?
Yes.
So you don't need any information from higher dimensional data.
Oh no, by the star, I mean all, you know,
No, I understand. Yeah.
maybe I'm not sure.
You don't need the link of an edge.
Right.
The link of a thing.
Well, you can tell the links of the edges. If you have the links of the stars, you can read off the star of, you can read off the link of every edge if you know the link of the vertices. So in some sense, it's all in there. But no, in this picture, we're in a natural sense, somehow, this integrand should live on the vertices. And we saw that in the last lecture as well. Okay, so just leave it like that. Okay. Now, so we handle, so now we know something that integrates to give a topological invariant. That's this formula here. What other things integrate to give topological invariants? I want to go over to the world go over to the world of Riemannian geometry, and let's go through the story there, and then we'll talk about combinatorial analogs of this. So it's kind of interesting. Historically, of course, Euler characteristic was found combinatorially first, and then the differential geometry side took a while to catch up. But then the differential geometry side jumped way ahead, and the combinatorial side is still trying to catch up. And so what do I mean by that? Over in the differential side, the next development was a ton of sort of topological invariants that could be constructed locally. And this goes under the name of characteristic classes. Okay? Skipping a huge amount of theory that started with Stiefel, Whitney, Pontryagin, Chern, and Weil. And I just want to present one version of this, which now goes under the name of Chern-Weil theory. What I want to do is consider all functions of this curvature matrix R which are invariant under conjugation. So trace of a matrix, trace of the matrix square, trace of the matrix cube, all these things. Usually in this theory we just choose a different basis for these homogeneous polynomials. So look at the characteristic polynomial of the identity plus t times r. And expand that out in powers of t, and you come up with a basis for the space of homogeneous polynomials. And so for sigma 1 is the trace of r, for example. And remember, r, and this is sigma sub I is homogeneous it's a homogeneous polynomial degree I in the entries, but the entries are two forms. So sigma sub I is a 2i form on M. The matrix R is skew, so the odd ones are 0, like the trace of R is 0. Right? Trace of R cubed is 0 because the matrix is skew. And now here's kind of number 2 is the main point. This number 2, that these forms in every degree, they're closed forms. So like we talked about last time, the closed differential forms represent de Rham cohomology classes. So from the curvature, we construct cohomology classes on the manifold. And the other key point is that the cohomology class, the form depends on the curvature, but the cohomology class of the form does not. Right? It just depends on the underlying differential structure. And these are what are called the Pontryagin classes of smooth manifold. The cohomology class is represented by these differential forms. Okay. So the bottom line here is just knowing the differential structure of a compact manifold, we get cohomology classes. But if you give me, in addition, a Riemannian metric, then I actually get canonical local representatives for these cohomology classes. So I can write them down in coefficients, where the coefficients are polynomials in curvature. Okay. So this is a great story, but I want to, localize our discussion now to not to cohomology classes, but remember we want some things we can integrate and just get a number. Okay, so a lot of what I'm going to say you can say more generally, but let's focus on things you can integrate to get a number. Okay, so the things you can integrate to get a number, these are called characteristic numbers. So what this says is if you take a bunch of these cohomology classes that we just constructed and take their cup product, wedge them together till you get something the dimension of the manifold, then you can integrate it if the manifold's oriented. Right? So now we have to start restricting ourselves to oriented manifolds. And this condition on the exponents just says exactly that it's the right dimension so you can integrate it over the manifold. So anything you get this way is called a Pontryagin number. Okay? So this is the definition that if you give me exponents, R1, ... so that when you wedge these forms together, you get something the same dimension as the manifold, and the manifold's oriented, then you can integrate these forms and get a number. Okay? Because the cohomology class of the form is independent of the metric, this number is independent of the metric. Right? The number that you get, if you tell me R1, R2, R3, that add up to the right dimension, then for every manifold of dimension 4n, this is how we're labeling things, for any manifold of dimension 4n, I get a number. Right? And that number depends only on the underlying differential structure. The integrand depends on the curvature, but the integral just depends on the underlying differential structure. Okay. And now one of the main, really big theorems in the subject is the Hirzebruch signature theorem, which says the signature of M is a Pontryagin number. Yeah?
Sorry, I just lost. What is this small pi of M?
That's the cohomology class that you get. That's sigma I of M.
Okay. Yeah.
Sigma I of R. Right. Right. So what I mean, the signature, if you have a manifold with dimension 4m, you can divide the cohomology right at the 2m point, and then the intersection form is a symmetric form, quadratic form on this, and so you can look at the signature of this form. So it's an integer. Okay. The signature of this manifold is a Pontryagin number. By what I mean, if you tell me what 4n is, I can take a linear combination of these things, a universal linear combination. It doesn't depend on the manifold. So that if you then evaluate this thing on any 4n dimensional manifold oriented, you will get the signature. Right? There's a universal formula. Okay. The signature is an integer. So here's what I mean. I mean, there exists for every r that satisfies the dimension count, there's some c sub r. So that if you add up all these things together and evaluate on m, but you get the signature. But c sub r is independent of m. It's just a universal collection of characteristic numbers. Okay. So this is already kind of remarkable, because what we know just from the start is that Pontryagin numbers are independent of the metric, but may depend on the differentiable structure. Right? But now suddenly we found out some collection of them is actually topological invariant, the signature. So this is kind of a remarkable fact. Another important thing to notice here is that a Pontryagin number, if you switch the orientation on a manifold, each Pontryagin number switches by -1. Because the cohomology classes are independent of orientation, but when we go to integrate them, we have to choose an orientation, and choosing the opposite orientation just gives us the negative of the integral. So these Pontryagin numbers change by -1 when I change the orientation, whereas the Euler characteristic did not. So just for future reference, if a function of manifolds changes by -1 when you change the orientation, we'll call that an oriented function, and if it's left invariant, we'll call it an unoriented function. Okay, so this is the Riemannian story. And now let's start making the transition to the combinatorial story. So some basic definitions. Say two simplicial complexes are combinatorially equivalent if they have isomorphic subdivisions. If you can subdivide one, subdivide the other, and get things that are completely isomorphic, they're combinatorially equivalent. We want to restrict attention to combinatorial manifolds. And a manifold in any category is something where every neighborhood is equivalent to the standard ball. And so I have to tell you in this category what the standard ball is. Okay? Well, it's equivalent to tell you what the standard sphere is. So we'll let sigma sub n denote what's going to be for us the standard n sphere in the combinatorial theory, and that's something that's the boundary of the n plus 1 simplex. So this is the standard simplicial model for the sphere. In fact, a combinatorial n sphere will refer to anything that's combinatorially equivalent to that. Okay? Anything that has a subdivision isomorphic to a subdivision of the boundary of an n plus 1 simplex. And then the key definition is something's a combinatorial n manifold if the link of every vertex is a combinatorial n minus 1 sphere. So if the link of every vertex is a standard sphere, it's equivalent to saying the star of every vertex is a standard ball. Those are equivalent statements. So in that sense, it's a combinatorial manifold. And that's equivalent to saying that the link of every simplex is a combinatorial sphere of the appropriate dimension. Okay. One of the key theorems connecting smooth manifolds to combinatorial manifolds is due to Cairns, and then certain ingredients were clarified by Whitehead. Every smooth manifold has a smooth triangulation. Every smooth triangulation of a smooth manifold is a combinatorial manifold. And every two smooth triangulations of a smooth manifold are combinatorially equivalent. So that's part one. So a smooth manifold actually has a unique combinatorial structure. Right? You triangulate it in a smooth way, and you get the structure of a combinatorial manifold. And if you triangulate it any other way smoothly, you'll get a combinatorially equivalent manifold. So up to combinatorial equivalence, there's a unique combinatorial manifold that's homeomorphic, that arises as a smooth triangulation. Let me say that. But you can go further, that you can get non-diffeomorphic manifolds which have the same underlying combinatorial manifold. And there are combinatorial manifolds that do not arise in this way, right? That are not the smooth triangulation of any smooth manifold. So they're slightly different categories, but there is a map from differentiable manifolds to combinatorial manifolds up to equivalence. Okay. Okay, so the next ingredient in our story is due to Tom and independently Rocklin and Schwark, that these characteristic numbers which we defined for differentiable manifolds the definition can actually be extended to combinatorial manifolds. So I'm saying it in kind of a strange way, but if you have any one of these p's, any characteristic number that's defined on closed-oriented differentiable n manifolds, then there's a natural function on closed-oriented combinatorial n manifolds which extends this. Part of this theorem then implies that the combinatorial number, that the characteristic number, which we said depended only on the differentiable structure, actually depends only on the underlying combinatorial structure. Right? If you triangulate it smoothly, the number you get only depends on the combinatorial manifold that results. And so you can get non-diffeomorphic manifolds that you know have to have the same characteristic numbers because they have the same underlying combinatorial manifold. Okay. So that's what I'm saying. In particular, so you can define characteristic numbers for combinatorial manifolds, and in particular, the characteristic number of differentiable manifolds only depends on the underlying combinatorial manifold. And then at the bottom, you can say much more. The first thing is that a theorem like this is true for all the rational Pontryagin cohomology classes can be extended to combinatorial manifolds. And moreover, Novikov proved that they're actually topological invariants. And he won a Fields Medal largely for this theorem. So, I love telling this story because first of all, there are a lot of great mathematicians involved, and it's just a beautiful history. Okay, so now let's start here. Here, let's just review where we are. So if M is a compact-oriented smooth manifold and P is a Pontryagin number, we see that we get a number without choice of a Riemannian metric. But if you give me a Riemannian metric, I get a canonical local representation for that number as an integrand. Okay? We also know that if you give me a combinatorial manifold, that number is well defined. And it only depends on the combinatorial equivalence class of the combinatorial manifold. Now, this means if you subdivide it, that number doesn't change. Okay? And now we want to kind of fill in the picture. So if you give me a differential manifold, I get that number. And if you give me a metric, I get a local representation. Well, if you give me an equivalence class of combinatorial manifolds, I get a number. The question now is, if you give me a precise triangulation, do I get a local representation for that number? Right? That's the analogous fact, if it is a fact. So the big question one is, are the Pontryagin numbers of a combinatorial manifold also locally defined? If I give you a precise triangulation, right, do I then get a local representation for a Pontryagin number? So let me be precise about what I mean by that. It's exactly the story we talked about for Euler characteristic. So what do I mean by a locally defined function? Suppose I give you a function that's defined on oriented combinatorial n-1 spheres. We're talking about oriented things. And the link, if you have an oriented manifold, then the link inherits an orientation. So suppose I have a function on oriented combinatorial n-1 spheres. Then we can construct a function on oriented combinatorial n manifolds by just going through the procedure we did for Euler characteristic. Evaluate this function on the link of each vertex and then sum them up. Okay, and that gives me a function on combinatorial manifolds. Any function arising in that way is said to be locally defined. So, for example, the Euler characteristic is locally defined. Okay, so now we can give an answer to question one. Are the Pontryagin numbers locally defined? The answer is yes. There are every Pontryagin number is locally defined in this way. So the first fact is it's true for the first rational Pontryagin class by Gabrielov, Gelfand, and Losik. So this, if you're talking about numbers, this is the case of a four-dimensional manifold. But in fact, it's true for all characteristic numbers. And this was proved by Levitt and Rourke with a big piece done by a completely different method by Cheeger. So let me just say something about this that, and again, this is true in greater generality that I'm saying it's true for rational Pontryagin classes, which I'm not talking about. I just want to focus on characteristic numbers. Levitt and Rourke, there are lots of ways to approach characteristic classes. Levitt and Rourke used the universal bundle approach. They constructed a universal bundle for characteristic manifolds and showed you can construct characteristic classes that way. Cheeger did a fascinating approach where he has a very sophisticated theory of spectral geometry of manifolds with conical singularities, Riemannian manifolds with conical singularities, which has broad applications. It's really a beautiful theory. And so anything that can be expressed in terms of sort of eigenvalues of an elliptic operator, he can study by his approach. And so his idea was you just take any of these characteristic numbers, which can be defined by looking at the spectrum of an elliptic operator, the signature being one of these. Okay? Then you start with a smooth metric and you deform it to this piecewise Euclidean metric. For each of these guys, we get some sort of integral that gives you the signature for each of the smooth ones. And using his theory, he could show that it converges to something. Right? It converges to something on this combinatorial thing. But both of these approaches are non-constructive. Both of them are existence theorems for this G that gives you the characteristic number. Okay? They don't tell you what G is. The only time, so that's the big problem too, is given a Pontryagin number, find G. Find this local function so that when you add them up, you get this characteristic number. I think that, in my opinion, this is one of the major problems in the study of combinatorial manifolds. It's a major question that's been open for a long time. So let me make some comments about it. First of all, there's an analogous question for rational Pontryagin classes. Find local representatives in the combinatorial setting, the way we did using curvature in the smooth setting. Secondly, even the only time we know an explicit formula is for the first Pontryagin class. So if you're talking about a number, it's a four manifold. So you say it's an explicit formula. What is this formula? The only example where it's been worked out is in a paper by a fellow named Milin, where he does the triangulation of CP2 found by Kuhnel that has 9 vertices. So it's a 9-vertex triangulation of CP2, and each of the vertices all have isomorphic stars, right? So you just have to calculate what G is for one star. And his paper is 40 pages long to do this one example using the approach of Gabrielov, Galfand, and Losik. So in principle, it's an explicit formula. But in practice, it's there's still a value in looking for another sort of representation for it that might be simpler to understand. Okay. And I wanted to mention work of Galfand, McPherson, and students of McPherson like Laura Anderson and Eric Babson, and Jim Davis has also done some work, and Daniel Biss. They have an extremely ambitious approach to this problem, which is rather than just attack this problem directly, they want to come up with a combinatorial reformulation of the entire theory. So start from the beginning and come up with a notion of a combinatorial vector bundle, and then come up with notions of combinatorial universal bundle, combinatorial characteristic classes for these combinatorial vector bundles, and then work your way up through the theory, find a combinatorial Chern-Weil theory, figure out which combinatorial vector bundle on such a thing is the combinatorial tangent bundle, ... And so a combinatorial version of the entire theory. And it's been there's been steady progress through this program, really remarkable progress. And most recently, Daniel Biss's thesis last spring, he proved that the category of combinatorial vector bundles is equivalent to the category of smooth bundles. I mean, they're sort of the same sets of objects. So it's made great progress, but there's still this question of which bundle is the tangent bundle. That's what you want to get your hands on. And so it has not resulted in any explicit formulas, at least as far as I know. So this big problem, too, is still completely open. And OK, so now I have a little convincing to do. Well, I want to claim that you can work on that big problem, too, without understanding everything I said up to this point. I ended the last lecture by saying you don't need to understand all of differential geometry to work on the Einstein metrics and Ricci curvature. And after the lecture, some people disputed this characterization. And I will say it certainly helps to either know some differential geometry or know some differential geometers. Okay, so that's certainly helpful. But I'm going to prove a theorem now. I want to show you something about this problem, and you'll see that if you just step back and stay calm, you can often do something. Okay, so we know that so what we learned there is that every Pontryagin number, the Euler characteristic obviously has a local representation. Every Pontryagin number has a local representation, right? But that doesn't answer the original questions: which functions have local representations? Okay, so let's present a theorem which actually, I hope to have a preprint available by now, but it's not just because I'm rewriting the introduction. But anyway, it's a relatively new result. So I just want to present a converse to the theorem of Levitt and Rourke. I should say Levitt and Rourke and Cheeger. So a function on the set of combinatorial n manifolds is a combinatorial invariant if it assigns the same number to combinatorial equivalent manifolds. So what we're looking for are ways to assign functions to oriented spheres. So when you add them up over the links of all the vertices of an oriented manifold, you get a combinatorial invariant. And so that any topological invariant is a combinatorial invariant. And the question is, what functions can you get? So the part one is relatively minor. It says if you want to check if it's a combinatorial invariant, it's enough to check that it assigns the same number to every sphere, every combinatorial sphere. It's a minor fact, but useful. And here's the main theorem, that any locally defined combinatorial invariant is just a multiple of the Euler characteristic plus a characteristic number. Okay? There are no other locally defined combinatorial invariants other than Euler characteristic and the characteristic number. So that's the set of things you can find out by looking at each star independently, assigning a number, and adding them up is precisely characteristic numbers and Euler characteristic. This was something like this, very much like this, was known for a while. Ed Miller, in his thesis, proved a theorem which has as an implication, if two smooth manifolds have the same Euler characteristic and all the same Pontryagin numbers, then there's no locally defined combinatorial invariant which distinguishes them. Okay? So our theorem refines that, saying the reason why there's no locally defined combinatorial invariant which distinguishes them is because the only combinatorial invariants are the Euler characteristic and Pontryagin numbers. So and moreover, this theorem works for this is a theorem about smooth manifolds. This works for more generally combinatorial manifolds. So in that sense, the theorem that I'm going to present also my theorem has a much simpler proof. I will say that his theorem is actually proved something much stronger in the setting that he proved. Namely, he said that he proved that if you have two smooth manifolds and they have the same Euler characteristic and all the same Pontryagin numbers, then there exists triangulations of this. There exists a triangulation of this one and a triangulation of this one and a one-to-one correspondence between the vertices, so that the corresponding vertices have isomorphic links, right? So that's a strong version of saying you can't tell them apart by local combinatorial invariance. But his proof is actually much, much harder. And so what I want to do in the remaining time is actually show you how to prove a theorem like this. Give you a sketch of a proof. Okay.
So is that theorem also true in the combinatorial setting, that if they have the same set of
His proof, I will say, his proof is unpublished, so I don't know all the details. And it's in the Harvard archives, where they don't like you to spend too much time looking at theses. So I've only looked at it and they don't like you to Xerox too much either. So I haven't really been able to read the whole proof. But his proof follows by, for every Euler characteristic and every Pontryagin number, he actually constructs a smooth manifold that has that data, and then shows, sort of works that way. And I don't know, and I don't think he knows how to do this in the combinatorial setting. If you have a combinatorial manifold with an Euler characteristic and Pontryagin number, construct a precise combinatorial manifold with that data. I don't. So his method of proof doesn't work. Whether the statement is true or not, I'm not sure. It probably is, if I had to guess, but I don't know. Okay. So let me show you how to prove a theorem like that. The theorem falls into two parts. I mean, you can take any function on manifolds and write it as an unoriented function plus an oriented function. Namely, define as, you can write its value on a manifold M as 1/2 f of m plus f of minus m plus ... And you get it, so you can write as a sum of an unoriented function, meaning one that does not change if you change the orientation, and an oriented function, meaning one that does change by minus some when you change the orientation. So it's enough to prove two separate theorems. One is, if you have a locally defined unoriented function, then it's a multiple of the Euler characteristic. And you have a locally defined combinatorial invariant which is oriented, then it's a Pontryagin number. I also want to say, although I won't have time, you can actually, the big problem is to figure out what G is, the local function. I won't do that, but you can say things about G in these two settings. Okay. So let's start with the oriented case, because this is actually kind of interesting by itself. So the theorem we want to prove is, if you have a locally defined unoriented function, so a function that does not depend on orientation, and it assigns the same number to every combinatorial sphere, then in fact it's just a multiple of the Euler characteristic. Moreover, the local function is just a multiple of that function E that we talked about before. There's uniqueness. If you define any function which doesn't depend on orientations, which when you sum it up gives you a number which is in combinatorial invariant, which is independent of orientation, is Euler characteristic, and the local function is that function E. Right? This is a really strong uniqueness theorem. It's interesting for a couple reasons. First of all, things like this were proved earlier by Levitt, and then I wrote a note that kind of clarified things, kind of weaker statements. That if you were looking at all simplicial complexes and you had a function which summed up to give an invariant, then you have this uniqueness. But that proof just didn't work if you restricted the case of combinatorial n manifolds. Moreover, this statement I just wrote contradicts some statements that appear in the literature. So in that sense, it's kind of interesting as well. And I think what the confusion is that what I'm saying is that this function E is unique. I'm not saying the formula I wrote for E is unique. Right? There are all sorts of identities, the Dane-Somerville relations you can use to rewrite the formula. But the function is unique. And I think that's the cause of the confusion. Yes, it's true for all n independently.
For n odd, it just says the function is 0.
Right, and that's the first step, is to show that for n odd it's 0. I also want to show this implies some really interesting things. For example, there's an old theorem, and actually I'm not sure who it's due to, but it seems that the only combinatorial invariant that you can write in terms of the number of the f vector, that you can write in terms of the f vector, is the Euler characteristic. The f vector being the number of faces of each dimension. Right? Because anything you can write in terms of an f vector, you can write locally by changing as a function over the length the way we just did. Right? So that's an old theorem. This implies that. but in fact it says something stronger. There's no function of spheres, right, that you can add up and get a combinatorial invariant other than that alternating sum. Okay, so here's how to prove it. The first step, and what our input is that it assigns the same number to every sphere. So the first step is to show that if it assigns the same number to every n sphere and n is odd, then in fact it's assigning the number 0 to every sphere. And so here's what I'm going to show you. The proof has no differential geometry. It's stuff that anyone here could have done. Okay, so let y be the common value that fg is assigning to n spheres. And let's consider the case n equals 1. Okay, so here's an example of a combinatorial one sphere. Right? The rule says fg on this one sphere is the sum of g applied to the link of each vertex. Each vertex has a link that's a 0 sphere, just 2 points. And so I get 3 times that function has to be y. Okay? Now I look at another. This is the standard one sphere. This is the boundary of the 2 simplex. And here's another standard one sphere, which is I take the standard 0 sphere and I take its suspension, meaning double cone. Right? So I take this other standard one sphere and I apply the same rule. I get 4 times whatever g is assigning to the 0 sphere. Right? And they have to be equal. Well, they can only be equal if g of this thing is 0 and y is 0. Right? The equations, too many equations. Okay. So if you're talking about n equals 1, it has to assign the number 0. Okay, now let's see what happens if we do n equals 2. Because it looks like we're almost implying that it assigns 0 to everything. So let's go through. There are a bunch of standard simplicial 2 spheres. One is the standard one, the boundary of the 3 simplex. All the vertices have the same length. There are 4 of them, and the link is the standard 3-vertex circle. So whatever this number y is, in this case, it's got to be 4 times whatever g is assigning to this link. Everyone know what I'm doing? It's here? Okay. Another thing you can do is take the standard 1 sphere, that triangle, and take its suspension. Okay. Now you apply the formula there. The 2 vertices at the end, I should point up here. The 2 vertices at the ends here have a linked triangle. So when I add up g over all the vertices, I'll get 2 times g of this thing. And 3 vertices have a link, a square. Like this vertex here has a link, this square. And so I'll get 3 times g of that. And so that has to be the same number y. And then I go to the last guy I want to look at is the double suspension of a 0 sphere. So I start with 2 points, and then I suspend that to get a square, and then I suspend that, right, to get this shape. And so there's 6 vertices, and the link of each of the vertices is a square. So I get this set of 3 equations and 3 unknowns. But in this case, the equations are linearly dependent, right? And so I can't conclude that it's assigning the number 0 to every 2 sphere, fortunately. And you can do this for every n and write down this system of equations where you get an equation for every, you can suspend an n minus k sphere k times. Look at the link. You write down all the equations. All of the links will be suspension of spheres. You'll get the same number of equations as unknowns, n plus 1. And then you can calculate the determinant of that system, and you get this, right? And it's non-zero precisely when n is odd, right? So you learn that when n is odd, the number it's associating in every sphere is 0. So it has to associate 0 to every sphere. Okay. Now we're ready to finish. So what do we know? Now we're still in this oriented invariant case. So now what we know is that there is a c. So it assigns the same number to every sphere. So there's some c so that that number is c times the Euler characteristic of the sphere. For that, we needed to know that the number was 0 for odd-dimensional spheres, since the Euler characteristic was is 0 for odd-dimensional spheres. But now we know in every dimension, no matter what number, in every dimension, there's some c, so that the number it's assigning to every sphere is c times the Euler characteristic. Then the conclusion is that that local function is actually c times that e. And therefore, the whole thing is summing to c times the Euler characteristic. And here, the proof is pretty simple. But once you get the main idea, that the idea from the last proof is let's keep looking at suspensions of things and build more complicated things out of simple things. So let's define a number associated to an n minus 1 sphere, capital N. S of n is the maximal integer k such that it's a k-fold suspension of something smaller. And then we'll prove that g of that thing is e of that thing by downward induction on this number. So for example, suppose that it happens to be the n-1 suspension of something. Well, then it has to be the n-1 suspension of a zero sphere to get the right dimension, so we know what it is. And now let M be the suspension of that. Then M is a combinatorial sphere, and we know that f of sub g of M is the sum over all the vertices of g of the link. But all the links are the same, right? Because it's just that it's an n-fold suspension of a zero sphere. So it has 2n plus 1 vertices, and all the links are equal to g. So when we apply I sub g to that, we get this. On the other hand, f sub g of M is equal to a constant times the Euler characteristic, and we know the Euler characteristic is given by summing E over everything. So just by comparing, we see for that sphere, g is equal to E times the appropriate constant. Okay. Now we just keep going by downward induction. So suppose you have some combinatorial sphere n, and it's a k suspension of something. Then let M be the suspension of that. And then the key point is so I've drawn the blue thing as n. I've drawn, here's n prime, some sphere. N is the k suspension of that, and M is the suspension of that. Okay? Now you just notice that every vertex here has link either n or a one higher suspension, right? And so by induction, everything that's a higher suspension is true that g equals E. And so by plugging into the equation, you can then solve for g of n, so it has to be E of n as well. Okay, so that's the proof. Okay. So now let's move on to the unoriented case, which is very different and involves some much more sophisticated math, but luckily we don't have to prove it. So it's the heroes in the subject, the giants in the subject have already proved it. Okay, so let's move on into the oriented case. Suppose f sub g is a locally defined combinatorial invariant, and it's oriented. If you swap the orientation on M, it swaps the orientation. The number changes by -1. We can write g as the sum of something oriented plus something unoriented in the same procedure. And look at this thing here. We decided that f was oriented, but this is the unoriented part of g. Well, if the local thing is unoriented, then the global thing is unoriented. So this thing is both oriented and unoriented, and so it has to be 0. Okay? But now, from what we saw in the last part is that if you have a function which is unoriented and assigns 0 to every manifold, then this is 0. We proved the uniqueness for the g. Right? So if f is oriented, this g sub u has to be 0, and that means that g is oriented. Okay, that's part 1. If f sub g is oriented, changes by minus sign when you flip the orientation on M, then the g has to be oriented. It's changed by -1 when you flip the orientation on the link. Okay. Now, okay, so now the next step is, what does it mean for two manifolds to be cobordant? Two manifolds are cobordant if their disjoint union is the boundary of a manifold of dimension 1 higher. So we want to do this in the combinatorial category, and we want to keep track of orientations. Okay? And now the next big step in this program is to say that if two manifolds are cobordant and you have any locally defined oriented combinatorial invariant, then it has to assign the same number to each of these guys. Okay? By the way, if it assigns the same number to every sphere and it's oriented, the number has to be 0, right? Because there are triangulations of the sphere which have orientation reversing isomorphisms, right? And therefore, anything with an orientation reversing isomorphism has to be assigned the number 0. Okay, so now we have an oriented, locally defined function on oriented manifolds. It assigns number 0 to every n sphere. We want to show it's invariant under cobordism. And now the proof, I'll show you the proof is relatively straightforward. I have this cobordism between M1 and M2. Let's cone off this cobordism at the end. And now this is no longer, it's a manifold everywhere except possibly these cone points. But everywhere else it's a manifold. We started with a manifold and then we just cone it off. Okay. Now, this W, this cobordism, is a manifold of dimension 1 higher. So if M is an n manifold, W is an n plus 1 manifold. So the link of an edge in W is an n-1 sphere. And those are the things we can apply G to. Right? G is a function on n-1 spheres. So define a 1 cochain by associating to every edge in W G of the link. And it's a 1 cochain. To check it's 1 cochain, we have to check that if you reverse the orientation on the link, that number changes by a -1. Right? And that's where we needed to know that G was oriented. Because if we change the orientation on E, that changes the orientation on the link. And because G is oriented, that flips the function by a -1. And so this really is a 1 cochain. Right? That it flips by -1 when you flip the orientation on E. Now let's take D star of that and push it over to the vertices. So if this is the edge E, and E is assigned the number alpha of E, then D star puts an alpha of E here and a minus alpha of E here and adds them up. There's actually kind of an awkward, why did I look at D star of this 1 chain? It's because somehow in the end we're talking about integrating 0 chains when you really should be talking about integrating n chains. That's what you integrate. So there's kind of a, anyway. Now the link of every edge is a sphere, and so G of it, I'm sorry, wait. So let's start over here. When I push it forward, I get a plus alpha here and a minus alpha here, and then I'm adding them all up. So let beta v be this whatever I get there at a vertex. If I add them up over all the vertices, I get 0. Right? Because I have a plus alpha here, a minus alpha here, and then I'm adding them all up. So it's going to all cancel out. So if I take this beta and I add them up over all the vertices, I get 0. But now what is the number that I'm associating to a vertex V? The number I'm associating to a vertex V is the sum of the alphas of all the links of the edges. But the link of an edge in the star of V is the same as the link of a vertex in the link of V. Right? So the number I'm associating to V is the sum over all the vertices in the link of G of that vertex. By definition, that's f sub G of the link. Right? So when I do this for every vertex in the cobordism, I get this total sum is 0. If the vertex has a spherical link, which is true at every manifold point, then the number associated to that vertex is 0. Okay? But everything's a manifold point except the 2 endpoints, the 2 cone points. And the 2 cone points have their links, my 2 manifolds. Right? So everything cancels out except those 2 guys at the end. Everything cancels out. I have 0 as the sum, but everything gives me 0 except the 2 guys at the end. So modulo some issues of orientation, I find out that those 2, they have to be the same, assigned the same number. OK. And now one more step is so we know that it's invariant under cobordism. The next step is to show that it's invariant under combinatorial equivalence, which I haven't proved yet. I just know it assigns the same number to every sphere. I now want to show that assigns the same number to combinatorially equivalent manifolds. Well, now it's enough to know that combinatorially equivalent manifolds are cobordant. Right? And that's really easy to see by Pochner's theorem, which tells you that if you have combinatorially equivalent manifolds, you can get from one to the other by relatively simple steps called bistellar flips. And so what you have to know is if you do a bistellar flip to something, the result is cobordant. Well, a bistellar flip, what that means is you take part of the boundary, so it's like sending this to this. That's like, think of this as the boundary of a triangle. I'm replacing one part of the boundary by the other part. All bistellar flips have this general form, that you replace one part of the boundary of an n+1 simplex by another. And that shows you how to build a cobordism. If you want to know that M is cobordant to what results from doing a bistellar flip, look at a cobordism from M to M. That's easy. And then just glue in an n+1 simplex that does the bistellar flip. It replaces this part of the boundary of the n+1 simplex by this part of the boundary of the n+1 simplex when you look at the boundary component. OK. So that shows that we've constructed a combinatorial invariant. And then the very last slide is that what have we done? We've shown that if it's an oriented, locally defined function which assigns the same number to every sphere, then it's a combinatorial invariant and it's a cobordism invariant. Moreover, it's obviously true that if you take a disjoint union, that what it assigns to a disjoint union is the sum, because it's the integral of something local. Okay. Well, you piece these things together, and you can summarize this by saying in fancy language that any such function is now a homomorphism from the rational cobordism group to the real numbers. Okay. That's exactly what this says, that if you take two copies of a manifold, which means disjoint union, you get two times the function. So this says it's a homomorphism from the rational cobordism group to the real numbers. And now you have to use a big theorem from Tom, who extended by Wald to the combinatorial category, that said any homomorphism from the rational cobordism group to the real numbers is a Pontryagin number. The Pontryagin numbers are precisely the homomorphisms from the rational Pontryagin group to the real numbers. And that says this number f that we've been dealing with is actually a Pontryagin number. Okay. So that's the proof, right? And that the only locally defined combinatorial invariants are Euler characteristic and Pontryagin numbers.
If you allow yourself to collect information from links of high-dimensional mixes, do you get anything?
Yeah, so for example, all of the rational Pontryagin classes, it depends what you mean. It depends how you interpret. Because you can read off the link of an. I mean, well.
I interpret it as follows. So you have someone sitting in the middle of the edge and sort of looking around, but not really walking much, but being able to communicate with you. And if on every edge you have somebody with a cell phone and calling you, so can you compute something more than dragging numbers and other things?
So it depends what kind of information you're allowed. So what I mean by that is rational Pontryagin classes have local representatives, which means, so not edges, but take four simplices. There is a way to attach a number to every four simplex, which just depends on its star, okay? So that what you're left with, the four chain you're left with, represents, I should have done n minus fours. No, the four cochain you just constructed represents the rational, the first Pontryagin class. So it's a cohomology class. It's not a number. Okay. That's part of what Levitt and Rourke proved. That's the first Pontryagin class is Gabrielov, Gelfand, and Losik. That there's a local number you can attach to every four simplex, so that four cochain you just constructed is the first Pontryagin class. But if you're talking about assigning a number so that when you add them up you get something, then that's a special case of this, because you can read off the link of an edge from the link of the vertex.
So your Ricci curvature yesterday for edge depended on more than just the link of that.
Yes, it depends on some kind of second neighborhood.
Right. So maybe that's what it is.
If you allow yourself larger neighborhoods, than just the star, then I don't know, and that's a good question.
That's not a large neighborhood, right? It's a different neighborhood.
Okay, well.
But you don't know that. So you sit you're sitting in the middle of the edge and you see things around, but you don't want to be in. But he's letting the person at the end.
Yeah, so the person who's standing at the end point of an edge knows the link of that edge. It lives in his link. Okay. So anyway, the final comment is, by doing these kind of simple-minded arguments, gluing things together and just see what happens, you can actually say some things about the G for these Pontryagin numbers. Nothing major, but you can say something. And so it's a small step towards us learning something about the answer to the big question. Yeah?
Earlier in your talk, you had this number that was m times m minus 1 down to m.
Yes, the weights that you needed to apply Garland's approach to a general simplicial complex.
Sometimes called the p plus 1 falling power of and it comes up in an important way in finite geometry, among other things. We're used to thinking of finite dimensional vector spaces as often having maybe a basis in powers of x.
There's not much of a comment I can make. I mean, its appearance in that formula is due to much simpler reasons. We just wanted a certain formula to be true involving the weight of a simplex and the weight of the things it's a face of. And so you just do, you know how many faces everything has. We're talking about simplicial complex. So it just showed up by counting the number of facets of a simplex. So, and then making sure that sort of those weights differed by exactly that number. So when we add them up, they sort of all cancel out. I'm in this setting. I mean, there may be a connection, I don't know. But in this setting, the reason it shows up is rather a simple-minded reason. So.
I can believe that you weren't thinking about the thing that I mentioned when you did it. But I would bet that if we were, if people here who have more expertise than I were to consider the two things together, I bet they would see something interesting.
Well, that would be very interesting. Yeah, Gunter.
All the invariants you were talking about at the end, they were always somehow rational numbers, real numbers, complex numbers, and so on. What about like Z2 invariants and so on?
Oh, yeah, so
Theorems, it's always only rational Pontryagin classes that you capture, and the other ones are more complex.
well, Z2 is somewhat easier. Those are Stiefel-Whitney classes, for which the sort of local formulas are been known for a long time. Yeah, so a homology class representing the dual of the Pieth Stiefel-Whitney class, you take the barycentric subdivision and add up all the n minus p simplices. And the integer Pontryagin classes are not determined. So there are a number of ways of saying it. The number that you calculate by doing this procedure to come up with a Pontryagin class might associate a rational number, not an integer, to the class. But also the story is kind of a long one. But you can take, for example, an integer Pontryagin class, and you know that this class is somehow extendable. You can define it for combinatorial manifolds, but it might not be an integer on a combinatorial manifold. It's one of the standard ways to tell that a combinatorial manifold is not smoothable. That you don't get an integer when you evaluate an integer Pontryagin class. In other words, a class that gives you an integer for smooth manifolds. So, I mean, the proof that these rational Pontryagin classes are PL invariants starts with Hirzebruch's theorem, that some combination is a topological invariant. And then you start using that to solving for different classes. By you have some linear combination, which is topological invariant, and then you want to solve for each individual class. But when you're solving linear equation, you have to start dividing by things, right, to solve for each class. And so you really can only work over the rationals.
But if you were attempting to do something in characteristic P, and you had a rational where the denominator is prime P, then in that case, that would assign an integer mod P to that rational.
Right, so the proof shows that the rational Pontryagin classes are well defined, and the question of what else might be well defined, or is a good question.